Hi everybody, my name is Jack and I'm a research fellow at Laurentia University. I'm a volcanologist by trade, but I tend to dabble in a few different areas. But today I'm going to discuss some of the key insights that detrital zircon can provide in terms of understanding sedimentation and magmatism across the North American craton. And fundamentally, this research wouldn't be possible without the support of the Metal Earth R&D program, which has been supported by the Canadian government, but also NSERC, Great Bear Resources and Kinross, who have been supporting some of my research up in the Red Lake Greenstone Belt. So zircon is a powerhouse in geochronology, in large part because it facilitates the calculation and verification of ages using multiple different isotopes. It crystallises over a large pressure, temperature and compositional range, and it's relatively resistant to low to medium grade metamorphism, and so it has high reset temperatures and high recrystallization temperatures. And it's considered to be chemically stable and relatively hard, so it's pretty resistant to physical abrasion in the sedimentary cycle, and it's often very well preserved in sandstones and conglomerates. And ultimately, zircon has been used to determine the long-term growth of Earth's continental crust, decipher the mechanisms for prehistoric environmental change, constrain the paleotectonic setting of metasedimentary belts, and also determine max step ages and provenance of sediments or metasediments, which I'll discuss a little bit more later. So over the last 2 decades or so, thousands of uranium-lead zircon ages have been published as part of various thematic and local regional scale mapping projects across the North American craton. And this data has variably been compiled by the provincial geological surveys, typically into province-bound databases, but Metal Earth has also developed an amalgamated database of sorts, which basically consists of geochronological data for much of the Superior province, which covers pretty much or a lot of Quebec, Ontario and the eastern part of Manitoba. And so if anyone wants to download that database, they can from the Metal Earth website. The analysis of zircon has also been integral to the Metal Earth program. So at the transect scale, uranium-lead dating has been used to constrain the crystallization ages of Archean volcanic and plutonic suites. It's also been used to constrain max step ages and provenance of zircons in some of these metasedimentary belts across the Superior province and also across the Slave province. And then at the province to craton scale, uranium, lead, hafnium, oxygen and trace element studies of zircon have been used to map crustal architecture and characterise the formation and evolution of Archean crust. And you'll hear a bit more about that today from Christine. So addressing some of these big craton scale questions surrounding sedimentation and magmatism often requires a lot of data, and that in turn is quite expensive. So it makes sense from a financial and also a time perspective to utilise as much existing data as possible. So as my first port of call, I downloaded all of the magmatic zircon data from the Metal Earth database and plotted the compilation of ages on a kernel density estimate plot, or a KDE plot. Essentially is the basis for trying to identify peaks in magmatism. And what we see is that there is a prominent peak at 2.7 billion years, and then a smattering of older ages from 2.7 typically up to almost 3.5 billion years. And on the face of this, it would suggest that there was a major magmatic event at 2.7 billion years. However, there is a need to address possible biases within this data set. In particular, is this magmatic zircon age distribution biased due to sample distribution? So the data set itself consists of a relatively low number of samples from the Northern Superior province, in large part due to inaccessibility. But it also consists of a large number of samples from the Southern Superior province, particularly the Abitibi sub-province due to its scientific interest regarding mineralisation, but also ease of access. And so one thing we can do to reduce this bias is by looking at the detrital zircon record, which essentially involves the analysis of zircon that was captured in sediments that were ultimately eroded from rocks over a regional catchment area. And so I went back into the various databases and quickly discovered that there were hundreds of detrital zircon samples published across the North American craton. But I also realised that the data is published in a variety of different formats, and for it to be useful, it ultimately needs to be compiled and standardised. And so I started compiling the data, but also then realised that the data there's large inconsistencies in the way the data is reported. So several data sets exclude measurements of uranium, thorium and lead concentrations. Likewise, the thorium and uranium ratio, which is often used to infer whether a zircon is magmatic or metamorphic in origin, is also often absent from some data sets. It's also worth noting that data collected via laser ablation ICP-MS is not often corrected for common lead. And there's also differences in reporting the analytical uncertainty of some of these isotopic measurements. So there's relative versus an absolute error, or one standard error versus two standard error. And then lastly, some of the isotopic ages were calculated using different decay constants and the natural isotopic abundance ratios of uranium. So I developed a standardised spreadsheet that aimed to capture the sample information and essential data that's typically published as part of detrital zircon studies. I then recalculated and normalised the analytical uncertainty values for every isotopic measurement to 2 absolute standard errors, which is pretty typical of most detrital zircon studies. And then I recalculated all of the detrital zircon ages for each metasedimentary sample using the same decay constants. And ultimately, once compiled, we ended up with a standardised database of detrital zircon data that consisted of 255 published samples, many of which were analysed by the people in this room, but also almost 24,000 zircon analyses, which, if analysed today on a typical laser ablation ICP-MS system, would likely cost more than $100,000. So it is important that we make this data more easily accessible, in large part so that researchers can use it and determine if it's actually useful for them. And so this map here basically shows the distribution of detrital zircon samples across the North American craton. So the samples in red represent data that's previously been published. It's data that's published in journal articles, government reports, or by the geological surveys. And the samples in yellow represent samples that were published or collected and analysed as part of the Metal Earth program. But today I'm just going to discuss the samples in red. So now that we have this database, we can start filtering the data and looking for patterns. And so this figure here basically shows the uranium lead age distribution of magmatic detrital zircon, which is detrital zircon with thorium uranium values greater than 0.1. And this plot consists of over 20,000 ages. It defines a peak at around 2.7 billion years, and then a smaller peak at 1.9 billion years. And this broadly corresponds to magmatism across the Slave Province and the Superior Province, at least with respect to the 2.7 billion year age, and also magmatism associated with the Trans-Hudson orogeny at 1.9 billion years. We can also plot the metamorphic detrital zircon. So this is basically a plot of detrital zircon with thorium-uranium ratios less than 0.1. And what we see from this sort of limited metamorphic record of 550 grains is that there was a metamorphic event between 2.7 and 2.6 billion years following the major sort of 2.7 magmatic event. And this event probably represents the amalgamation of the various sub-provinces of the Superior Province. There's also another small peak at 1.9 billion years that's associated with the Trans-Hudson orogeny, and then another peak at 1.1 to 1 billion years related to metamorphism in the Grenville Province. We can also sort of further subdivide this data, and we can plot the uranium lead age distribution by geological province, so of the North American craton. And what's most notable is that the Slave Province and the Superior Province are each defined by a 2.7 billion year peak that likely corresponds to greenstone belt volcanism and TGG magmatism. The 2.7 GA peak is also recognisable in sediments from the southern and the Grenville Province, but in this case it likely represents detritus that was eroded from the Superior Province. There's also a consistent 1.9 GA peak in sediments from the Bear Province and the Churchill Province that likely reflect magmatism associated with the Trans-Hudson orogeny. And then finally there's a 1.1 to 1 billion year peak in the Southern Province that's most likely associated with the formation of the mid-continental rift system that's defined by present-day Lake Superior. So at this point it's worth coming back and comparing the magmatic zircon age distribution that I originally extracted from the Metal Earth database and comparing that with our newly compiled Detrital zircon data from the Superior Craton. And what we see is that they are near mirrors of each other. So it probably means that both data sets provide a pretty good foundation for understanding magmatism across the province. It's also possible to compare our newly compiled data with global Detrital zircon databases. So here I've replotted the 200,000+ Detrital zircon age compilation from Puets to basically show that the major peaks in the global record are also comparable to what we see in the North American Craton, and that these peaks also tend to coincide with major supercontinent cycles. We can then compare the temporal occurrences of Canadian VMS deposits with the apparent peaks in the Detrital zircon record. And what we see is that the VMS deposits of the Abitibi Greenstone Belt formed during that broad 2.7 GA magmatic event. The VMS deposits in the Flin Flon Belt on the border of Manitoba and Saskatchewan also formed around 1.8 to 1.9 billion years. And this is broadly associated with the Trans-Hudson orogeny, but also more broadly the formation of the supercontinent Columbia. Now this apparent correlation isn't all that new on a global scale. And in this 2015 paper by Peter Kaywood, he basically showed that a lot of VMS deposits, nickel copper sulfide deposits and orogenic gold deposits all broadly tended to coincide with the formation of supercontinents. And so it is worth questioning whether the Detrital zircon record is actually real. Does this reflect magmatic events, or is it simply an artefact of preservation? And so we can see on this figure on the left, also by Peter Kaywood, he basically showed that crustal preservation was greatest during continental collision, so during the formation of these big supercontinents, while crustal preservation was relatively reduced in convergent plate margins such as subduction zones or in extensional settings. And so this is ultimately something we'll have to consider going forward. Regardless, moving on, another major focus of the Metal Earth program was deciphering the geodynamic origin of the metasedimentary subprovince of the Superior Province, and I've highlighted them in yellow here. And one of the key questions is, for example, are these belts forearc or foreland basins? Did these basins form in extensional settings? Understanding some of these nuances is quite important because they ultimately have implications for understanding the potential for mineralisation in these belts. But in terms of my research or my contribution to this project at the moment, I am using our newly compiled Detrital zircon data to provide some temporal constraints on sedimentation in the form of maximum depositional age. And so again, the samples in red represent data that's already been published in journal articles or in government reports, and the samples in yellow represent samples collected and analysed as part of the Metal Earth program. So as it turns out, maximum depositional age isn't all that simple. There are currently 12 different methods for calculating max dep age, and there's no real consensus on what the best method is. But it is important that we choose an appropriate method because some methods have the potential to produce anomalously young maximum depositional age. And this is pretty best exemplified by the newly discovered Great Bear deposit up in the Red Lake Greenstone Belt. And so here mineralisation is hosted by a sequence of felsic porphyries that intruded into a metasedimentary deposit sequence that was adjacent to a big crustal scale fault called the LP fault. And the discovery of gold within the LP fault zone is quite significant because the geology here was previously interpreted to have been part of this so-called Confederation assemblage, which was interpreted to have been barren in terms of mineralisation. However, there were no real geochronological constraints to confirm such an attribution, so we ultimately wanted to provide those constraints. So what we did is we went and sampled 2 felsic porphyries from the LP fault zone that intruded the metasedimentary deposit sequence. And so the first felsic porphyry, it's a very silicified altered felsic porphyry called E32A, and we analysed this via TIMS. We've got a zircon age of approximately 2730, plus or minus around 4 million years, although this age is likely xenocristic in nature. But we also analysed another felsic, less altered felsic porphyry, a quartz feldspar porphyry, and this returned a very precise age of 2722 plus or minus 1 million years. And so this is quite significant because it provides a minimum age constraint on sedimentation because it intruded the sedimentary sequence, but it also means that the stratigraphy here is not actually part of the Confederation assemblage, but more likely a much younger assemblage such as the Graves assemblage, which has been dated at 2732, or more likely the St. Joseph suite, which has been dated at 2725 to 2717. And this suite has also been known to host gold mineralisation. But keeping in mind that 2722 age, we then dated 3 metasedimentary samples from the LP fault zone. And what we found is that pretty much every sample had a uranium-lead peak of around 2730 to 2720 million years, which is pretty consistent with the age of the felsic porphyries. However, every sample also contained a series of these anomalously young detrital zircons that probably reflected the influence of lead loss associated with hydrothermal alteration. But if you include these, all these zircons were still all concordant, and it becomes difficult when they're near the max depth age to exclude them on purpose. You don't want to exclude any data that's ideally concordant. But if you apply the various max depth ages to this data, including these anomalously young ages, you'll get max depth ages that are younger than the felsic porphyry that ultimately intruded the sequence. And so it just means that ultimately we have to be somewhat conservative in our estimates of max depth age, especially for rocks that are Archean in age and may have experienced extensive alteration. Regardless, for the purposes of this presentation, we've just decided to apply this recently developed model by Peter Vimich. It basically calculates this so-called maximum likelihood age using radial plots, and it's been implemented in isoplot R, and it's very quick and simple to calculate. And so this map basically shows the maximum likelihood age for every published sample or metasedimentary sample from across the Superior Province. And what we can then do is provide a very basic contour of those ages. And so in general, the maximum likelihood age of these metasedimentary basins appears to decrease in age towards the south. There could be 2 realistic reasons for this. The first is that it could indicate that the metasedimentary basins form sequentially towards the south over a period of 20 to 30 million years. Alternatively, it could be interpreted that these basins formed all at the same time, with the apparent shift in maximum likelihood age simply reflecting the differences in sediment sources across the province. The only real way to address this question will be to compile data that provides a minimum age for sedimentation. So such as we did at the Great Bear property, we dated the felsic porphyries that intruded the sedimentary sequence, but it's also possible that we can date metamorphism and deformation. And so going forward, I'll be compiling some of these minimum age constraints to provide better constraints for sedimentation across the Superior Province. Another interesting feature is that the detrital zircon age distributions for samples from the different metasedimentary belts are all pretty similar. So they're all defined by this zircon peak at 2.7 billion years, and then a smattering of much older zircons, typically from 2.7 to 3 billion years. And so over the last decade, several models have been proposed that basically suggest that the detrital zircon age distribution reflects the tectonic setting in which these sediments were ultimately deposited. In particular, Peter Kaywood suggests that sediments with a large proportion of near depositional zircons were most likely deposited in convergent settings, while sediments with a large zircon age distribution or bimodal age distributions more likely reflects deposition in an extensional setting. Although it is worth noting that such models were originally developed for modern Earth tectonic settings, typically Paleoproterozoic or younger. Regardless, these models have been used to infer the geodynamic setting of older Archean metasedimentary belts. And often the common interpretation by applying these models is that every metasedimentary belt in the Archean is convergent in origin. Ben Froman, who produced a nice paper in 2017, he basically suggested the same thing based on the abundance of near depositional Neo-Archean zircon within the Pontiac subprovince and the Abitibi subprovince. And there is some evidence to support this. So we have deep crustal reflection seismic profiles across the Superior Craton that preserve these dipping features that offset the moho. There's also Archean TGGs that may have formed by melting of subducted oceanic slabs, although it is worth noting that each of these two observations can be explained via different means. But David Moll also, who was a research fellow at Laurentia and is now at Geoscience Australia working as a geochronologist, he basically suggested that there was a transition in tectonic processes at about 2.7 billion years. So a transition from more Archean type tectonics to more modern Earth tectonics. And he attributed this to a change as a function of various geochemical data. Regardless, more recently there's been a paper by Zhu who basically proposed that a largely numerical model that suggests that the abundance of near depositional zircon that would be typical of convergent settings could also be explained by a variety of different Archean tectonic models, such as stagnant lid or heat pipe cooling. And so ultimately, if we take these sort of 5 representative samples from across the Superior Province and then plot them on these 2 plots by Kaywood and Zhu, what we find is that the data can be explained by either deposition in a convergent setting or deposition as a function of Archean tectonic processes. And so ultimately, one of the key takeaways from this is that we're realistically unable to use either diagram unless we have firm constraints on the geodynamic setting in which sedimentation originally took place. And it's also worth noting, though, that the applicability of such models is pretty questionable in Archean terrains in general, due to the limited range of zircon ages that are preserved in the Archean. Regardless, it's also worth noting that there is quite a bit of evidence that some of these metasedimentary deposits were emplaced in active magmatic environments, which is typical of more extensional type tectonic settings and Archean tectonic models. So we have syn-sedimentary komatiitic volcanism associated with the Porcupine assemblage in the southern part of the Abitibi subprovince, and Adrian and Taus also discovered syn-sedimentary komatiites and peperites in the Pontiac subprovince. There's also intrusive rocks that are comparable in age to the youngest detrital zircon in the Pontiac subprovince. And there's also a relatively short time span between the end of sedimentation and the onset of low pressure, high temperature metamorphism in the Pontiac subprovince. And lastly, there's very few characteristic indicators for subduction zones, including blue schists, eclogites or ophiolites. And so ultimately, this suggests that some of these metasedimentary basins probably formed in an extensional tectonic setting, possibly as a consequence of Archean tectonic processes. And thank you. If anyone has any questions, I'm happy to take them.